All right, cool. So how did part two of lesson 4 go for everyone? The language modeling task.
Well, I had the feeling that it's modeling language is really just one big categorical variable.
It went fine for me. I basically just followed along the notebook, and as I've always been doing, just trying to understand each of the steps. I did find that there were a few things, you couldn't just run the notebook straight. You had to, like, some things were kind of out of order, and you had to load the English library for the tokenizer and things like that. So there were a few little gotchas, but other than that, it seemed to get the results that he demonstrated.
Mm-hmm. Has anyone tried to apply the language modeling stuff to another data set yet? Yeah, I haven't gotten there either, although I definitely aspire to do that. It seems like a really interesting technique. Has anyone gone through any of the demos where they train a model like this and use it to produce new text? I guess kind of like what he did in the archive notebook. Did anyone run through the archive notebook? That was the one called Language Model Archive, I think. I have not run through it, but he went through it briefly in the lecture video where he gets it to, like, he changes the category and gets it to, I think, produce a new abstract or something like that based on the category that he proposes.
I found that, I at least looked at that and found that oh, sorry.
Whoa. Yeah, I think you've got 2 audio connections maybe, Nick?
No, I think that was someone else actually.
Oh, okay.
Okay. I was just going to say that the loading that data set wasn't quite as straightforward as the IMDb data set. There's a few options shown, and I think that accessing the data requires a little more experimentation.
Yeah, I'm looking at it now in the notebook, and it doesn't. There's no link to the data or anything like that. Did you have to find where it was in the forums and then pull it down?
Yeah, I'm not. I think I must have. Yeah.
Okay.
I didn't actually get it to run. I'm training my IMDb data set as we speak.
Okay. All right, cool. So in the Slack, Kai proposed the idea of in each of these sessions having one or multiple people spend a few minutes to kind of share some of the things that they've learned or go a little bit deeper on one of the topics that's related to what we're covering. And I think Kai was going to talk about embedding matrices and one-hot encoding. Was anyone else going to do something like that? I think Joey, I don't know if Joey is on, but Joey in the Slack mentioned something about RNNs.
Does not seem that he's on in the list.
All right. Well, Kai, do you want to jump into your mini presentation?
Yes.
Would you like to share the screen, or?
Yes.
Okay.
Do I just have to click the button here?
You should.
Okay.
If it doesn't take it from me, I'll stop sharing. Well, I guess I can do that anyway.
Can you see it, or?
Yep.
Okay. Okay, so I really just made some handwritten notes. Okay, the first thing is that I want to do a little reminder of. I mean, Jeremy showed that in the course, but what computationally happens in this kind of dense neural network. And I kind of want to connect that to this node representation. I think this is something that everyone has, a picture that everyone has in mind, I think. So in this case, you have a dense neural network with 8 input values, 8 input neurons here. This is here you put in the values into the network, and then a hidden layer with 16 neurons, and then another hidden layer with 8 neurons. And what each of those neurons is doing is really just summing up those values in the first input layer with a weighted sum, and adding something like a ReLU or any other kind of activation function. It's also adding a bias, but to simplify it, we will not have a look into this bias term. It's just an additional addition in this case. And so every neuron here is creating a weighted sum of those values here, and then applying a rectified linear unit or whatever, and outputs one number, and that's going to the next layer and the next and the next, and until you eventually have something like a softmax layer or whatever you want to get out of the network. And what you mathematically do is a matrix multiplication. And so when you have these 8 values you put into this network, you may do a matrix multiplication with all the weights in these edges here. You kind of arrange them as the matrix. So you have 8 inputs and 16 nodes in the next layer. And that's why you have 8 times 16 weights. And when you do this multiplication, you get out a 16 long vector. This is kind of how a matrix multiplication works. Then you apply the rectified linear unit or any other activation function, and in the next layer you do the same. And then you have 8 neurons in this layer, and until you eventually have any output values. So just as a reminder, what's mathematically happening when you put in numbers into a neural network. Is that somehow clear to all of you?
Yes.
Okay. So, yeah, or any question or no? Okay. So in this case, in this first case, there are continuous numbers. So continuous variables. And when you have factor variables, you have to do, or classically you did something what's called one-hot encoding. And this is an example with weekdays, the same that Jeremy had in the lecture. And you really just encode, when you have a factor variable with 7 instances, like weekdays, you have a 7 long vector, and you put in a 1 for Monday in this case here, and in the second place for Tuesday, and so on, and all the other values are 0. So that's just different representation of Monday to Sunday. You do that because you don't want to have an ordinal scale in this data, because I mean, for weekdays there is kind of an ordinal scale, because Tuesday comes after Monday and Wednesday after Tuesday, but the difference, for example, between Friday and Saturday is another than Wednesday and Thursday, for example. So when you do this one-hot encoding, you don't have this ordinal scale, because a neural network naturally would take this into account, this ordinal scale, and you don't want to have that. It's more clear when you have something like names or movies you watched, for example, then there is no scale in this kind of variable. And you end up with a very big sparse vector. In this case, for seven weekdays, it's not very big, but when you have what's called a high cardinality, so a lot of instances, not just 7, then you end up with a very big sparse vector. And what you do when you put this into the network is really the same what you would do with continuous variables. You put in the 7 numbers into the network, have a matrix multiplication with the weights of the first layer. So 7, because you have 7 numbers and 30 neurons. I just chose this number, it's randomly chosen. And you get out a vector with 30 values. And then you apply ReLU, go on and do the same thing in the next layer, and until you eventually have your output softmax or whatever. Okay, so, and then let's have a look at this matrix multiplication in detail, what's happening here. That's what I'm showing here. So when you multiply this with the weight matrix, this is kind of an intermediate step you have. You multiply each row with each of these values, and so every row where you have a 0 is going to be 0 here in this intermediate step. And as you can see, it's really just picking one row of these values. In the case of Tuesday, you really just pick the second row of these weights, and everything else is 0. But what you do in a classical neural network is really you do this multiplication and you add up all those numbers until you get this vector here. But I mean, this is very inefficient. You can see that this is really inefficient. You are doing a lot of multiplications and additions you don't have to do, because the output is really just the second row here in this matrix. And this is what Jeremy was referring to as a lookup table. You can solve this by really just looking up the second row in this weight matrix. And the same thing is for Wednesday. When you have Wednesday, it's picking the third row, and Sunday the seventh row. So there's really no need to do that. And so you can use this weight matrix as a embedding matrix, and later on really just pick this row. And I kind of understand this as a computationally efficient little neural network you put in front of your actual neural network. Because the numbers you get out here, you replace this one-hot encoded vector with the numbers you get out here, and put them into your neural network in your actual neural network. But this is also a small, efficient neural network, because it's a linear layer. It's basically a linear layer optimized for one-hot encoded vectors. Does that somehow make sense? And you train it, so you train this embedding matrix just like you would train a normal layer in a neural network with a backpropagation. But you can do it much more efficient when you know that for an instance where you have Tuesday, you only have this one row of weights. Everything else is for sure going to be 0. So,
hey Kai.
Yeah.
First of all, thanks for picturing the weight matrix as the network diagram. I hate it when people just throw out matrices without the network diagram. Secondly, when you say it's picking the second row of weights, I actually think, do you think it really, do you mean you're picking the second column of weights?
No, in this arrangement, I think it's row. You can turn it around, the matrix, and then you pick a column. That's actually, I think, in the courses from Andrew Ng, he's doing the weight matrix the other way around. So you can flip this matrix and then you pick columns. But I think in this case, you would choose a row.
Mm.
Yeah.
Oh, well, if you're doing the whole multiplication of, the vector times the entire matrix, I think you're picking the column. I don't know. In America, we actually would write the weight matrix on the left and the vector on the right. Maybe that's the confusion here.
No, you're right. So when you just flip this here, flip this matrix and flip this matrix, and then you would pick a column. Yeah. Okay. Yeah, actually, then it's not the correct form of matrix multiplication. You're right. So it's better to flip it around and choose columns. Yeah.
Okay. Thank you.
Yeah.
Hi, Kai. Can you hear me?
It's a little
faint, but
try again.
I've not tried to do the mic on it before, so I'll try and speak up. Can you hear me now?
Yeah. When you speak up a little bit, maybe.
I'll try. The only thing I weren't sure about, it's not been mentioned by Jeremy. I get the whole principle of it all, but if you did the full matrix multiplication, so the matrix you're using for the one-hot encoding, which is ultimately an identity matrix, if we included that in the backpropagation, would it try to change it from being an identity matrix to have other elements that aren't just one? Are you with me?
Yeah, I know what you mean, but actually I don't have a clear picture in mind of how backpropagation or how training of this embedding matrix works. I really just looked up how you path data through this embedding matrix and how it's connected to the to your actual neural network.
I mean, Jeremy seems to. It kind of says the same. He says that obviously this is purely an optimization, which is correct, but that would be on the assumption that the other matrix cannot be modified. If you just use matrices as opposed to picking a row out. It was never mentioned, and I better read around, and I've not seen it mentioned either. I just wondered if you knew whether it could try to change Monday ultimately to be, you know what I mean, to share value, so they can all share values. At the moment, there is one row per day, which is per category.
I mean,
whether it could change.
So when normally you would have continuous variables here, and in the case of this one-hot encoding scheme, you know that there is only one in this vector and everything else is 0. So it's clear that one row or column, when you flip around the matrix, one column is pretty much reserved for Tuesday, for example.
Yeah, that's our starting values. But that's what I mean is because I can appreciate in this data that Saturday and Sunday, the embedding matrix may try to learn something that says on a weekend it is important. So like when he takes the dates and times and says whether it's a bank holiday and whatever else, whether the network would try to learn that Saturday and Sunday actually have something in common and would therefore start to share values out of the embedding matrix. And then what you would see is that Saturday and Sunday don't have a single unit element. They'd have maybe, you know what I mean, they would start to share elements of the embedding matrix. I don't know if it's been mentioned anywhere, but that was the only thing that kind of confused me by doing this optimization process. Would we be losing the ability for the network to learn new features as opposed to just the information that we were kind of given it? You know, we're kind of forcing it to just have one row. So we're making the data for Saturday non-overlapping with any of the other days.
Yeah, well, I think so for Saturday and Sunday to have something in common does not mean that they have to share weights.
Yeah.
And I don't think.
They don't share weights when we start it out. I just wondered if the learning process, if the matrix was there, could the matrix start to, like I say, be non-identity basically?
Yeah. Actually, I don't know.
Yeah, I don't really understand the reference to the identity matrix. Are we talking about the one-hot encoding?
Yeah, because obviously, because we've got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and it's a 7x7 matrix. It ultimately just ends up being an identity matrix.
Yeah.
It doesn't have to be, but the way in which we've organised it, that's how it would be perceived in the you know, our flow of matrices multiplying. Initially, that's how it would start out as identity, but
yeah, but I think you don't have this kind of identity matrix and put this into the network because this vector represents one data point, and the next can be Friday, and the next can be Friday again, and then you have Saturday, and then you have Saturday again, and then Sunday maybe. It's not. Right. There's not an order when you put this into the network.
Yeah. I get that it doesn't have to be in order, but I wouldn't have. So yeah, I don't know where you would stand for having. I forgot what it's called. It's for the cardinality value. You would have more elements than you would specific types. You know what I mean? Friday, having 2 Fridays in there doesn't seem to make much sense. Are you with me? But yeah, it doesn't have to be identity. I was just using it because it looks like an identity matrix. That's all.
Yeah, I mean, when you list Monday till Sunday, you have this identity matrix, right?
Yeah. I was just wondering, by omitting it out of the learning process, are we preventing it from actually being changed? Because that's what we're doing as an optimization.
Yeah, maybe one way to think about it from Jeremy's lecture was, or either Jeremy's lecture or Rachel's article was that you can kind of think of the the weights as being weightings of some kind of embedded factors that the matrix the embedding neural network understands and figures out. And so from that perspective, you know, if you've got kind of this cardinality, like this 30, you know, it's basically like these 30 features that the network is relating each of these days to. And so in a sense, all of these days are kind of relating back to some 30 embedded features that this network is trying to, that you're training this network against. So from that perspective, it is kind of capturing relationships from one date to the next, but relative to these underlying features. Does that make sense?
Yes, I do get, I get what you're saying, and I get this whole principle, and I suppose that, like I say, I get how the embedding matrix is finding the relationships in the high dimensional space that they can share. It was more by doing this process, it was an optimization, but you are ultimately taking a matrix out of the system. And obviously, in none of our networks, other than our input layer, do we have any weights that don't change when you unfreeze it all. So by taking it out, you would be changing how the network would learn. I suppose that obviously what we're trying to do is learn all the features in the embedding matrix, but if you also had this matrix, would it put some of the features into that matrix?
No, I think the training process is working exactly the same than in a normal neural network. It's really, I mean, this is just, this embedding matrix it's the same thing mathematically with like this layer here. So it's basically just attaching a linear layer up front of the neural network. And when you do learning, you pass it through the complete network until you reach this embedding matrix, and you're learning these weights. And in the end, you, I don't know if the learning process is actually getting better because you're using this embedding matrices, or if you can computationally get around this here, but it's mathematically speaking the same. It's just like if you would train a small neural network in front of the actual neural network to represent your weekdays.
But the embedding neural network, is that always trained separately, or is it ever, have you come across any reference of it being trained kind of end to end with the rest of the network?
I think it's always trained end to end.
Because what we did, what we loaded it from static.
Yeah,
right?
because you can use it pre-trained.
Was that when we load it from pre-train, is that just initialization and then we continue to train it, or was that we're loading the static embedding matrix that we use in training the rest of it?
Yeah, I just looked up the video 1 hour ago, and Jeremy said that there are 2 ways to initialize this matrix, this embedding matrix. The one thing is randomly, which is just the same you would do in a neural network, so random weight initialization. And you can also use a pre-trained network. So especially for this kind of variables, Monday till Sunday, when someone already trained this on a retail data set, for example, this embedding matrix kind of catches the concept of weekdays for retail. And then you can use those weights as an initialization, or even, I don't know if you freeze it, but you use that as your initialization, because it already has this concept of weekdays for retail.
Okay.
So, and when you, I think it's, I did not do much NLP stuff, but that's what you do when you use kind of this pre-trained embedding matrices for language models. You load them from a pre-trained, I think this word to vec thing. That's, yeah.
I think, in terms of language, word to vec, pre-training makes sense. Getting the pre-trained data weights makes sense, but I'm not sure about weekdays. I mean, you can have some businesses where It's
Yeah.
strong on the weekdays and weak on the weekends. And then if you use that if you use those weights for business that are strong on the weekends and bad on the weekdays, that's a bad idea.
Yeah,
So,
I agree. Yeah, I agree. Yeah.
Yeah.
But that's the example that Jeremy had in the lecture, the weekday example. Yeah. So he said that if at your company someone already trained such an embedding matrix for your stores, then you can use that in a different model.
Sorry, can you hear me?
Yes.
So I got a simple question. Just so the output from the embedding matrix is the 30 nodes, like
No, 30 values, just 30 values coming
30
out.
values.
Yeah.
Yeah.
Sorry, no, I can't hear you. No, he's gone.
He's muted.
No, I just said thanks.
Okay.
Any other questions for Kai on this?
just thanks, Kai. I appreciate you clarifying this one hot encoding stuff up.
Sure, no problem. That was good for me too.
Yeah, same here.
Do you have any insight on how long that vector needs to be? I know Jeremy gave some information during the lecture, but it kind of seems like they come out of the blue.
Yeah, they are. I mean, Jeremy said something like half of the instances you have, but at max 50, I think.
Yeah.
And that's kind of, it's the same like for almost any parameter you have in deep learning. It's kind of a witchcraft thing. I don't know.
I just don't know if you were using it, like if you were running into problems training, like what would drive you to say, oh, I need to increase the length of that vector or something like that. I don't know how to measure its performance.
Yeah. I don't know. I actually don't know. I think that's really, Jeremy did that for so many years, and that's what he feels is a good value, I think.
Yeah, I think it ends up being just another hyperparameter, and if you run out of other things to play with, you can try playing with that.
I think 30 is too much for weekdays. I don't know why I chose this number, but yeah.
So would I be 3 or 4? Because there are seven days of the week, and so half of 7 is like 3 or 4. Is that how that would be for the day of the week?
3 or 4? What do you mean?
Because that's the way I understand. So you have the number of days of the week is 7, right? So if you take half of that, is 3.5. So you choose like either 3 or 4, right?
Yeah, I think you would use 4 maybe. Yeah, it should not be 30. I think 4 would be better. I think Jeremy had 4 for the weekdays in the lecture. So that's 30 is a little bit too much, I think, for weekdays.
But is it so you start with 100 encodings and then you go through or you start with that vector of 4, that's your representation, and that's what you feed into the network, is it?
So what you do is create this embedding matrix from scratch. You don't have to do all the steps here because that's what you want to avoid, right? So all these computations you don't have to do, multiplying 0 with some numbers and adding zeros together, you don't need to do that. So you directly initialize this matrix randomly if you start and don't have something that's pre-trained, and then the training is done just like a normal layer in a neural network, because it's basically the same like a linear layer in a network.
Yeah. Mm-hmm.
So what I don't know is if there is any special way of training this layer to be more efficient compared to of this kind of representation for a layer. I don't have a look into that. Okay. Any more questions? Okay.
All right. Thanks again, Kai.
Thank you.
No problem. So I think next time maybe we'll try that again with this poll. And I think this time it was just one day. Maybe there are more people jumping in on that.
Yeah, that would be great. So as we're going through the lessons, the lesson 5, think about, it'd be great if everyone thought about areas that they, you know, might be useful to kind of dig a little bit deeper in and prepare a couple minutes of sharing. That would be fantastic. I think Kai set the bar really high, but in his description, he said it only needed to be like 3 minutes. So don't be scared away. Cool. So what other questions or stumbling blocks did folks run into with the language modeling stuff? Anything that hasn't come up yet?
So there were, for me, there were a couple of tweaks that were needed in the code, right? So it didn't run as it was. So nothing major, but a couple of things. And the other thing that it was running for quite a while. So one iteration through learning took like 20 minutes on the setup I had. So I didn't finish that. So because he had like 16 cycles. So that's 16 times 20 minutes. It's quite a lot. So I think I need to upgrade to a faster machine on a Google Cloud.
Yeah, mine is still running. I thought I had it all I thought I had it all finished up, and I realized that there was a stupid error because he tried to load something before he actually saved it. And so I didn't get it all the way through. So it's running now.
Yeah.
So I ran out of memory on the GPU, and I ended up scaling back the batch size, and I made it work. Does anybody have any idea how you can sort of a priori figure out like how much memory a model might take to avoid running out of memory during a run? Maybe optimizing the batch size?
Yeah, I haven't come across anything that suggests that there's any science to it. I guess you would think that there should be, right? Since it's, you know, the number of parameters in your model, and you know the number of weights, and that should all translate into some memory requirement, modulo, you know, some internal optimization that the thing is doing. But I haven't seen that. And Jeremy, in the earlier lessons, he seemed to suggest that you just keep dividing it in half until it runs or something like that, like some kind of binary search, you know, manual binary search in the batch size space. Has anyone come across anything more, some kind of methodology for that?
Yeah, Sam, can I just, can you hear me?
Yes.
No, I think you said it right. It actually depends on the size of the network. When I say network, you will have an input layer, you would have an intermediate layer, and you would have an output layer. And so the number of neurons in these layers, number one. The other issue would be whether, you know, what size of what is the size of your floats? You know, is it 16 bit? Is it 32 bit? Is it 64 bit? So there are some calculations which are available, and then also it depends on number of epochs you're running, and what is the size of your input data. So actually it can be done mathematically, but I don't see any reference to the within the Fast.ai library. If I find something, I will put it on the Slack channel. But it's actually doable. Because what really happens is, if, you know, in real life, let's say if you are actually training hundreds and millions of parameters, you know, and if you're using parallel architectures, you would need to do this because, you know, you run into very sizable computing costs otherwise. So I'm sure there are heuristics and there are ways of, estimating it. If I find something, I'll put it up.
Okay, great.
That would be a great feature in the library. Just
Yeah.
as a method maybe, or
I mean, if you could pre-compute that number, roughly, it could just be automated. You wouldn't even have to select the batch size.
yeah.
Mm-hmm. Kind of just solve for the maximum batch that you can fit into your GPU memory.
Yep.
I guess that will require, the library to also, to be fine-tuned with the operating system on which it is running. So it actually really depends on the efficiency of the library and nothing else. So, your code efficiency has to be very, very good for that to happen. I'm sure it will evolve because, what we don't realize is that, Fast.ai is really a very, very new library. It's been in, it's actually been in development for not more than last 15 to 18 months. And
by the way, does anyone know if this is an actual maintained project? Because I made a proposal a week ago maybe for documentation, and it seems that it's not maintained at the moment.
You mean Fast.ai?
Yeah.
Well, I get the notifications from the GitHub page of Fast.ai, and they have a lot of stuff going on. Maybe they are so busy they didn't respond to you, but
okay.
There's a lot of stuff going on. I get like a couple of 5 to 10 emails a day that there's something going on there. Someone posted an issue, someone fixed an issue, someone did something. So I think they do quite a lot, and I think it's a bunch of people that does the work. So, but they could be, maybe they need your help with that documentation. So that's great.
Did you submit your proposal as a pull request, or is it?
No, I started with an issue before I created the pull request because I basically delete the old documentation stuff and create a new one. So I wanted to create an issue first.
If you can find out where the developers communicate with one another, other than there, like in a Slack channel or something, you might be able to raise it there.
Yeah.
Yeah, probably the forums, I would think. I don't know.
Yeah, maybe.
Slack.
I'll post it in the forum. Yeah, that's a good idea.
Yeah, the other idea that I had for this, and it's kind of above my pay grade from a programming perspective. I don't know if it's doable, but it strikes me that when I'm going through these notebooks, I'm probably spending, who knows how many hours looking at a notebook where the GPU isn't involved. And I wonder if there's some way to build something into Jupyter Notebook so that I guess the problem I'm trying to solve is, is there a way to run my notebook on a regular cheap CPU instance and have it only call out to a GPU when it actually needs to do that? So somehow virtualize the GPU. I talked to a company yesterday that does parts of that. This company called Bitfusion that allows you to virtualize your GPUs. But it would be kind of interesting to somehow build that into some part of this, into either Jupyter or into the library or something like that.
I think they have a environment file for CPU. Maybe you can use that on your local machine and then try to push that to your, what are you using, Paperspace or Google?
Using Google now.
Yeah, and then push it to Google when you're finished. I don't know. So in the GitHub there is an environment file for Conda, which is titled environment-CPU, I think.
Okay.
So maybe you can use that one and use the library with CPU. Because you can use PyTorch with CPU.
I built a Docker container that is a CPU-only version, and I'll typically use Paperspace, and for the language modeling, I'll use that to train it because it takes quite a bit of GPU power to train it. But afterwards, if you want to play around, you can just sort of download the model and then play around with it offline, sort of.
Is there any way to besides from saving models, to somehow, if you go through all this kind of data processing stuff, is there a way to save kind of the entire state of everything you're doing in a notebook and then ship it someplace? Or is that just the notebook file?
I did play around a little bit with that, but I don't think anything I saw saved the state of the GPU. It'll, like, there are some utilities that allow you to basically save the state of the Jupyter notebook, you know, I guess whatever's in RAM, all the data structures and so on. But and I think it works if you're running on the CPU only version, but I don't think it'll work trying to save it from the GPU instance. Like I tried it a couple times, didn't work. So
okay. Well, if you got any pointers on specific libraries or tools that you were playing around with, that might help me kind of think through how to do something like that. I appreciate it. All right, cool. So other thoughts, stumbling blocks, interesting observations from this lesson? We don't have David here to tell us about what's coming next. I guess he already did. It sounds like lesson 5, we start to go deeper into the internals of PyTorch. Well, looking forward to it. Someone said earlier the extra week was helpful.
yeah, definitely. I think it was useful. Yeah.
Good. Yeah, it was useful for me too. I didn't. If we were on lesson 5, no, I wouldn't have gotten any of this language modeling stuff. All right, cool. Any other thoughts, questions?
No, I think. Sorry.
Go ahead.
No, go ahead.
I was just going to say, does anybody know enough about developing models in PyTorch directly, and like how difficult it would be to take something that you develop with, you know, Fast.ai and then just run it under PyTorch? I know it's a layer on top of PyTorch, but it's just like the Fast.ai library, if you load it up, it's like it's kind of very heavy. And I want to see if there's a way to kind of take advantage of the tooling it provides you to train something, but then at sort of like production, not have to have that entire thing.
I think when you save a model, it's just the same than if you would save it with PyTorch. I don't think that they created an own representation of models. They have this classes that are kind of stuffing a lot of stuff from PyTorch and some utilities together for modeling. But I think when it comes to the model itself, it's pure PyTorch.
Right, but there's the entire infrastructure for like loading data sets, or so if you're trying to feed data into it, you have an alternate means of feeding data into it than, you know, what Fast.ai does.
Yeah. So you would have to create this whole pipeline for yourself, I think.
Right. Okay.
Yeah.
Just wanted to share the observation that I think entity embedding matrices, Kai did a good job in terms of explaining the mathematics behind it. But, you know, the intuition in the real world is quite, I think is quite important, because people need to understand, you know, what is the size of the entity embedding matrices. And if you, I don't recall in which lesson, I think either in video 4 or video 5, I think it's there in video 4 only, where what happens is, you know, all the entities that are a part of your model. For example, if you see the movies and the user review database, you know, both the user embedding and the movie embedding are passed as a single row to the network. So what I'll do, Sam, is I'll try and dig around, you know, the real world intuition of embedding, you know, the entity matrices, and if I feel that I can present something on that, I would love to do so. I'll put it up on the Slack, because I think the real world intuition is important. Yeah.
I actually heard a very good example for getting an intuition what embedding matrices can, what they represent. Sam, I hope you're not disappointed, but I heard that at the NVIDIA AI podcast. So there was, so in this language models, you have something that's in psychology that's called, I think, imperative association test. I think that's what it's called. And there, you give people words and they kind of connect them together. I don't know how it exactly works, but you can get out of this test how people connect concepts. Like, for example, biases like that man and career is connected like woman and family, for example. And so you kind of see this in this test. And when you apply these tests to these embedding matrices by really just looking at the distances from the vectors, you see the exact same bias that humans have, because it's trained with language that is created by humans. And so it really kind of captures these concepts that people have in mind into this embedding matrix. So when you would look at the distance between man and career and woman and family, it would be the same as you would find in this imperative association tests. And that's pretty, I find that very interesting and impressive, that you kind of capture this concept that people have in mind when they, yeah, the language that they have in mind, yeah.
You know, what I would tend to do is I would tend not to, bring in word embeddings when we discuss entity embeddings, because it, I humbly believe it confuses a lot of people. For example, one of the persons on the chat just now said, like certain, in the retail business, certain stores do well on weekdays and certain stores do well on weekends.
Yeah,
now,
but I mean, this is
yes,
the same thing. It's not only mathematically the same, but it's basically the same thing, because words in a text are really just if one factor variable with a very high cardinality, and so you don't have just the letters in a word, but a word also has kind of something like a concept, and that's also true for weekdays in retail or for any other factor variable you would have. So it's the concept is basically the same.
Yes, absolutely right. From a real world angle, people usually have more data which can be used for entity embeddings, so of course this data or the knowledge is actually not very structured. It's available, but it can be used as a useful pointer for creating the entity embeddings. My point was that not many people are aware of NLP models and the latest, for instance, word2vec or cloud. So for people who are not coming from an NLP background, sometimes it confuses the thought process, because entities are very simple. A customer is a customer, a store is a store, a salesman is a salesman. These are real world entities. Each of these entities have got certain for example, even if you see the example which has been given in one of the tutorials, there is a simple there is a dog and there is a puppy, and there's a cat. Now within each of the dog and the cat, there is one factor which could be called as a youthfulness factor. So in case of dog, it becomes a puppy. So I think most of the real world entities have a lot of knowledge which actually gets recognized as factors. So let me compose my thoughts on this. Then it will make more sense to make it simpler, because I think it's to me, entity embeddings is one of the most important things which I have learned from this course, which is not actually there in any other course. That's my viewpoint.
Yeah,
I'm looking forward to seeing what you come up with, because I was about to ask before you started speaking on it, if how the relationship between kind of the word to vec, the word embeddings and the entity embeddings relate, and if it's a one-to-one correlation. So it'd be interesting to hear your thoughts on that in more detail when you've had a chance to run through it.
Yes, I'll come in from the from the real world example. I will not take NLP examples, because I think it's much more simpler. See, just to share a minute, every entity has got what we call as a static type and a dynamic type. A static type is a behavior which is fixed. For example, a male is a male, a female is a female, you know. But dynamic type could be a job. Today I'm a banker, tomorrow I could be a programmer, you know, I could be an accountant. Now these are two different types, but both these different types affect my affect my characteristics as an entity. So what I'll do is I'll try to compose my thoughts on this, and you know, when I'm ready, then I'll post a message. And if folks are interested, then we could probably, I could spend a few minutes, you know, in one of the future sessions on the same.
Cool.
Great.
Kai, do you want to start another thread for next week, or do you want to keep just adding on to that thread?
We can start a new thread, I think, so that
Okay.
we can keep track of it. Yeah.
All right, thanks. All right, cool. Anything else before we wrap up? All right, well, awesome, everyone. Thanks as always, and catch you next week and in the Slack.
Yeah, thank you.
Thank you, Sam.
Guys.
Thank you, everyone.
Bye.
Thank you, Kai.
Thanks, Kai.
Thanks again, Kai.